Look up at the night sky, really look at it. What you see is just the tiniest glimpse of a universe so vast, so mysterious, it defies comprehension. Every star, every galaxy, even the blackest voids between them hold secrets we're only beginning to uncover. Take the Hubble Deep Field image, for instance. That single snapshot, no bigger than a grain of sand held at arm's length, revealed thousands of galaxies, each one a swirling island of stars, planets, and possibilities. And yet, that's just the tip of the cosmic iceberg. What lies beyond? What strange, unfathomable phenomena lurk in the darkest corners of space, places where the laws of physics seem to bend and break? The universe is far stranger than fiction. Imagine regions where matter is so densely packed it defies logic. Black holes wandering aimlessly through the cosmos, invisible dark matter weaving an unseen web that holds galaxies together, or eerie voids so empty they stretch for hundreds of millions of light years with almost nothing inside. These aren't just ideas from a sci-fi novel. They're real, documented mysteries that scientists grapple with every day. And today, we're diving deep into 25 of the most baffling enigmas the cosmos has to offer. From the ghostly whispers of dark energy to the mind-bending reality of rogue black holes, each one challenges everything we think we know about space, time, and existence itself. This isn't just a journey through science, it's an expedition into the unknown, a chance to stand at the edge of human understanding and peer into the abyss where answers only lead to more questions. So, if you've ever stared up at the stars and felt that tug of curiosity, that longing to unravel the universe's greatest secrets, you're in the right place. Buckle up, by the end of this, the night sky will never look the same to you again. We begin our journey into the cosmic unknown with the greatest ghost story ever told: dark matter. Picture the universe as a grand puzzle. Scientists can measure its weight, its shape, even how fast it's expanding. But when they tally up everything we can see, stars, planets, gas, it accounts for less than 5% of what should be there. So where's the rest? Enter dark matter, the invisible glue holding galaxies together. Its presence is undeniable. You can't see it, touch it, or detect it with any telescope, yet its gravitational pull is so strong. It bends the very fabric of space-time, twisting light from distant galaxies like a cosmic funhouse mirror. Without it, galaxies would fly apart, stars would scatter, and the universe as we know it wouldn't exist. So what exactly is this mysterious substance? Theories abound, each more fascinating than the last. Some scientists believe dark matter could be made of WIMP, weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. Others speculate about actions, ultralight particles flowing through the universe like an invisible river. Then there's the mind-bending possibility that dark matter isn't a particle at all, but a sign that our understanding of gravity is fundamentally flawed. Could Einstein's equations need rewriting? The debate rages on. The hunt for answers is anything but theoretical. Deep underground, shielded from cosmic noise, experiments like the LUX Zeppelin project are listening for the faintest whisper of a dark matter particle colliding with ordinary matter. In space, telescopes map the distorted light of distant galaxies, tracing dark matter's hidden fingerprints. Every failed detection, every unexpected signal, brings us closer to unraveling the mystery or realizing just how little we truly understand. One thing's certain, solving the enigma of dark matter wouldn't just fill a gap in our equations. It would rewrite the story of the universe itself. If dark matter is the universe's invisible scaffolding, then dark energy is the enigmatic force tearing it all apart. Discovered in 1998 by two rival teams of astronomers, this mysterious phenomenon sent shockwaves through the scientific community. They were studying distant supernova, the explosive deaths of massive stars, expecting to confirm the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The cosmos wasn't just growing larger, it was accelerating, as if some unseen hand was pressing harder on the gas pedal with every passing moment. What could possibly defy gravity's relentless pull? The leading explanation is the cosmological constant, a term Einstein once called his greatest blunder. It suggests empty space itself contains energy, a repulsive force that grows stronger as the universe expands. But here's the catch. Calculations predict this energy should be 120 orders of magnitude stronger than what we observe. That's like expecting a whisper and getting a supernova. Alternative theories abound. Quintessence, for example, proposes a dynamic energy field that fluctuates over time, unlike the steady cosmological constant. Some models even suggest dark energy could be a sign of extra dimensions bleeding into our own. But the truth is, no one really knows. The Euclid Space Telescope, launched in 2023, aims to change that. By mapping the distribution of galaxies and measuring how their light bends over billions of years, Euclid could reveal whether dark energy's strength has changed over cosmic history, a clue that might crack the case. One thing's clear: dark energy isn't just a curiosity. It's the dominant force in our universe, making up nearly 70% of its total energy. If it continues unchecked, it could eventually stretch spacetime so thin that galaxies, stars, even atoms are ripped apart in a distant future called the Big Rip. For now, though, it remains one of physics' greatest puzzles, a reminder that the cosmos is far stranger and far more dynamic than we ever imagined. Now let's shift our gaze to one of the cosmos' most unsettling gravitational mysteries, the Great Attractor. Imagine the entire Milky Way, along with thousands of other galaxies, racing through space at over 2 million kilometers per hour, not outward from the Big Bang, but toward a single, invisible point in the constellation Centaurus. This isn't science fiction, it's reality. Lurking about 220 million light-years away lies something so massive, its gravitational pull overrides the expansion of the universe itself. Yet for decades, its identity remained hidden behind a cosmic curtain, the zone of avoidance. The name sounds ominous for a reason. This region of the sky sits directly behind the Milky Way's dense disk, where thick clouds of dust and stars block nearly all visible light. It's like trying to spot a lighthouse through a blizzard, but just because we can't see it doesn't mean we can't sense it. Galaxies on the far side of the zone exhibit bizarre, coordinated motion, as if dragged by an unseen hand. The Great Attractor's presence isn't just a hunch, it's written in the trajectories of countless celestial bodies. So how do you study something hidden behind a galactic blind spot? You look in wavelengths invisible to human eyes. X-ray telescopes like NASA Chandra and Japan's Suzoku have pierced through the Milky Way's veil, revealing a sprawling cluster of galaxies called the Norma cluster at the heart of this anomaly. But here's the twist: even this dense cluster isn't massive enough to explain the staggering pull we observe. It's as if we've found a footprint but can't see the beast that made it. New research suggests the Great Attractor might just be a waypoint in an even larger cosmic current. Beyond it lies the Shapley supercluster, a gargantuan assembly of galaxies whose combined gravity could be yanking everything toward it, including our mysterious attractor. But the plot thickens. Some models hint that dark energy's influence might eventually overpower these titanic gravitational tugs, turning the universe's largest structures into isolated islands adrift in an ever-expanding void. For now, the Great Attractor remains a humbling reminder. Even as we map the cosmos, some forces refuse to be neatly explained. They tug at galaxies, rewrite trajectories, and challenge our understanding of where and to what we're all hurtling through the darkness. Rising from the heart of our galaxy like twin titans, the Fermi Bubbles are among the most colossal structures ever discovered, and you've likely never even heard of them. These enormous, hourglass-shaped lobes of gamma-ray light stretch 25,000 light-years above and below the Milky Way's disk, forming a cosmic hourglass that could swallow our entire solar system 1,000 times over. Discovered in 2010 by NASA, a Fermi Gamma-ray space telescope, they glow with the energy of 100,000 supernova, yet their origins remain one of the most heated debates in astrophysics. What could possibly create such gigantic, energetic structures? The prime suspect sits right at the galactic center, Sagittarius, a star, the supermassive black hole anchoring our Milky Way. Picture this black hole, 4 million times the mass of our Sun, going through a violent feeding frenzy sometime in the past, devouring vast clouds of gas or even entire stars. The resulting energy would have blasted outward in opposite directions like a cosmic fire hose, carving out these immense bubbles. Simulations suggest such an eruption could have occurred as recently as 2 to 4 million years ago, a blink in cosmic time. But there's another contender. Some scientists argue the bubbles might be the aftermath of a frenzy of star formation near the galactic core. When massive stars are born in dense clusters, they live fast, die young, and explode as supernova, collectively unleashing enough energy to inflate these gargantuan structures. The bubble's symmetrical shape and sharp edges, however, lean toward the black hole explanation. Stellar winds would likely create messier, more irregular formations. Here's where it gets even stranger. The bubbles aren't just empty shells, they're filled with fast-moving particles and tangled magnetic fields, acting like giant particle accelerators. This could explain why they glow so brightly in high-energy gamma rays. Even more puzzling, recent observations reveal faint, X-ray emitting chimneys connecting the bubbles to the galactic center, like cosmic umbilical cords feeding energy into them. The implications are staggering. If the Fermi bubbles were indeed sculpted by Sagittarius, a star's outburst, it means our galaxy's heart isn't the quiet, well-behaved giant we once thought. It's capable of violent, eruptive episodes that reshape its surroundings on a scale almost beyond comprehension. And if star formation is the culprit, it challenges our understanding of how galaxies evolve, revealing how even local stellar births can have galaxy-wide consequences. Right now, telescopes from radio to gamma-ray wavelengths are scrutinizing these structures, piecing together their history like detectives reconstructing a cosmic crime scene. Each new observation brings us closer to answering whether the Fermi bubbles are the scars of a black hole's tantrum or the aftermath of a stellar baby boom, or something even more exotic we haven't yet imagined. One thing's certain, these silent, luminous giants are forcing us to rethink how galaxies live, breathe, and occasionally erupt. Imagine a whisper so powerful it crosses billions of light years, a burst of radio waves so intense it outshines entire galaxies for just a fraction of a second. This isn't the plot of a sci-fi epic. These are fast radio bursts, or FRB, some of the most baffling signals in the cosmos. First detected in 2007, these fleeting pulses last mere milliseconds, yet pack as much energy as the Sun emits in 80 years. They arrive without warning from random directions across the sky, and then vanish just as quickly, leaving astronomers scrambling to unravel their secrets. What could possibly produce such extreme, short-lived flashes? The leading suspect is a magnetar, a type of neutron star with a magnetic field so strong it could strip the information off a credit card from halfway across the Milky Way. Picture one of these cosmic powerhouses undergoing a starquake, its crust cracking under unimaginable magnetic stress, releasing a shockwave of energy visible across the universe. In 2020, astronomers got their first solid clue when an FRB from our own galaxy was traced back to a magnetar eruption. But here's the twist, not all FRBs fit this mold. Some repeat at irregular intervals, while others fire just once and go silent forever. Then there's the elephant in the room. Could some FRBs be artificial? The idea isn't as far-fetched as it sounds. Their precise frequencies and staggering energy output have sparked speculation. Could these be cosmic lighthouses or even propulsion beams from advanced civilizations? While most scientists dismiss this as unlikely, the truth is we can't rule it out entirely. After all, history has taught us that dismissing cosmic anomalies too quickly can lead to missed discoveries. The real game changer has been Canada's CHIME telescope, a sprawling array of metal cylinders in British Columbia that acts like a cosmic net, catching hundreds of these elusive bursts. Unlike traditional telescopes, CHIME doesn't move, it watches the entire northern sky at once, turning FRBs from rare oddities into a data goldmine. Already, patterns are emerging. Some repeating bursts show a strange periodicity like clockwork, hinting at orbital motion around a companion star. Others arrive with a telltale twist in their radio waves, suggesting they've traveled through dense magnetic fields near black holes. But perhaps the most tantalizing clue lies in what FRBs carry with them. As these signals traverse the cosmos, they interact with the sparse electrons between galaxies, leaving a fingerprint of their journey. By decoding this, scientists are mapping the universe's missing matter, the invisible web of gas that makes up half of all atoms but had eluded detection until now. Every new FRB is a message in a bottle from the distant universe, written in a code we're only beginning to crack. Whether they're the death cries of collapsing stars, the sparks of cosmic collisions, or something even more extraordinary, one thing's clear: these millisecond mysteries are forcing us to rethink what's possible in the radio universe. And with thousands more being discovered each year, the next burst could be the one that changes everything. Among the countless stars in our galaxy, one stands out not for its brilliance, but for its bizarre behavior: KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this seemingly ordinary star has baffled astronomers since 2015, when the Kepler Space Telescope revealed its impossible light patterns. Most stars dim predictably when planets pass in front of them, but Tabby's star didn't follow the rules. Instead, its brightness plunged erratically, sometimes by a staggering 22%, as if something colossal and irregular were blocking its light. Theories erupted faster than solar flares, the most tantalizing, a Dyson sphere, a hypothetical megastructure built by an advanced civilization to harness a star's energy. Imagine a vast swarm of orbiting solar panels, blotting out starlight in chaotic, uneven patterns. It was a mind-bending possibility, one that made headlines worldwide. But science thrives on evidence, not speculation, and as researchers dug deeper, less exotic explanations emerged. Dust turned out to be the prime suspect. Observations from the Hubble and Spitzer telescopes revealed that the dimming varied across different wavelengths, consistent with fine particles scattering light, not solid megastructures. The star's infrared glow also suggested a dusty environment, likely from shattered comets or planetary debris. Yet even this explanation left gaps. The dust required would be immense, far more than our solar system contains, and its irregular distribution defies typical models of circumstellar material. What makes Tabby's star truly unique isn't just the mystery, it's how that mystery evolves. Unlike most astronomical puzzles, this one plays out in real time. Amateur astronomers worldwide contribute observations, catching unpredictable dips that professional telescopes might miss. In 2017, the star dimmed again, sparking a global observing campaign. Data revealed the dips weren't symmetrical, hinting at uneven dust clouds or even ringed planets with complex formations. Then, in 2021, another surprise: the star's overall brightness increased, something no dust-based model predicted. The truth might lie in a combination of factors: a young star with a chaotic debris disk, a family of eclipsing asteroids, or even interstellar material drifting through our line of sight. Or perhaps, just perhaps, there's still room for something more extraordinary. Tabby's star remains a cosmic Rorschach test, reflecting back our own assumptions about what's possible. Every new observation chips away at the mystery, but the bigger picture remains tantalizingly out of reach. One thing's certain, in a universe full of wonders, this star reminds us that sometimes the most ordinary-looking objects hide the wildest secrets. One summer night in 1977, a radio telescope in Ohio picked up something extraordinary, a signal so peculiar, so perfectly aligned with what scientists predicted an alien broadcast might look like that an astronomer scribbled, "Wow." In the margin of the data printout, that single word gave the wow signal its name, and nearly 5 decades later, it remains one of the most tantalizing and frustrating enigmas in the search for extraterrestrial intelligence. This wasn't just random cosmic noise. The signal blasted through the hydrogen line frequency, 1420 MHz, a quiet channel natural sources rarely use, precisely where scientists had speculated advanced civilizations might transmit. It lasted 72 seconds, the exact duration the telescope could observe that patch of sky as Earth rotated. Most striking of all, its intensity spiked and faded smoothly, just as you'd expect if it came from a distant point in space. But then nothing. Despite countless follow-up searches, the signal never repeated. So what was it? Over the years, theories have swung from the extraordinary to the mundane. Some proposed it was a military satellite transmission, but declassified records show no such craft were in position that night. Others blamed passing comets specifically. 2 icy bodies called 266P and 335P, which happened to be in the area decades later. The idea was that their hydrogen clouds could emit similar frequencies, but calculations showed their signals would have been far weaker than what was detected. Then there's the glitch hypothesis. Could it have been an earthly signal reflected off space debris, or a brief equipment malfunction? The telescope's design made that unlikely. It used 2 receivers that alternated every few seconds, and only one caught the signal. If it were local interference, both should have picked it up. The signal's purity also argued against noise. It was narrowband, laser-like in focus, unlike the messy static of natural cosmic sources. Modern efforts haven't given up. In 2020, astronomers used the Green Bank telescope to scan the same region, hunting for any faint echo of the original signal. They found silence. Meanwhile, projects like Breakthrough Listen scour millions of radio channels daily, hoping to catch another wow, but so far the universe hasn't obliged. What makes this 72-second blip so haunting isn't just its mystery, but its timing. It arrived just as humanity was beginning to seriously listen for cosmic neighbors, a fleeting hello that slipped away before we could answer. Whether it was a passing comet, a bizarre instrumental fluke, or just maybe a distant civilization briefly flicking on the radio, the wow signal stands as a monument to curiosity. It reminds us that the universe is vast, strange, and full of moments that defy easy explanation, moments that keep us looking up, wondering if we're truly alone. Most black holes announce their presence with terrifying flare, devouring stars, bending light into fiery rings, or powering blazing quasars, but not all play by those rules. Some lurk in the cosmic shadows, drifting silently between the stars like phantom predators. These are rogue black holes, cosmic ghosts ejected from their birthplaces and set adrift in the darkness. Imagine an object several times the mass of our Sun, compressed into a space smaller than a city, moving undetected through the galaxy, without an accretion disk of glowing gas or a companion star to strip material from. These solitary black holes emit no light, no X-rays, nothing to betray their location. They're the ultimate celestial stalkers, invisible unless they cross directly in front of a distant star. That's where Einstein's genius gives us a way to spot the unspottable. When a rogue black hole passes between us and a background star, its gravity warps space-time like a magnifying glass, bending and amplifying the starlight in an effect called gravitational microlensing. For days or weeks, the star brightens in a telltale curve, a cosmic flare revealing the unseen monster's path. The Hubble Space Telescope has caught a handful of these events, including one in 2011 where a star in the Carina constellation mysteriously flared, its light distorted by what researchers now believe was a rogue black hole roughly 7 times the Sun's mass, drifting alone through the Milky Way. But how do black holes end up as cosmic nomads? One leading theory points to supernova kicks. When a massive star collapses, asymmetrical explosions can launch the newborn black hole at speeds over 1 million kilometers per hour, fast enough to escape its home cluster or even the galaxy itself. Astronomers have traced the trajectories of some hypervelocity stars, their breakneck speeds hinting at past encounters with these gravitational slingshots. There's another, more exotic possibility: primordial black holes. These ancient relics might have formed in the chaotic microseconds after the Big Bang, when dense fluctuations in the infant universe collapsed directly into black holes without the need for dying stars. Some could be as small as asteroids, others as massive as stars, all wandering undetected for billions of years. If they exist, they'd solve multiple cosmic puzzles, from the nature of dark matter to the origins of supermassive black holes found unexpectedly early in the universe's history. The hunt is accelerating. Projects like the Legacy Survey of Space and Time at the Vera Rubin Observatory will scan the sky for microlensing events, potentially uncovering thousands of these invisible drifters. Each discovery could rewrite our understanding of gravity, stellar evolution, and the hidden architecture of our galaxy. Because here's the unsettling truth: right now, as you look up at the night sky, one of these stellar ghosts could be closer than the nearest star, a dark, silent voyager passing unseen through the cosmic night. At the edge of our solar system, far beyond Neptune's icy reign, something massive is pulling strings, twisting the orbits of distant objects like a cosmic puppeteer. For years, astronomers have tracked a peculiar pattern in the Kuiper belt, that ring of frozen leftovers from the solar system's birth. Most of these objects dance in predictable paths, but a handful defy expectations, their orbits tilted and clustered in a way that shouldn't happen by chance alone. The math points to one tantalizing explanation: a hidden planet, perhaps 10 times Earth's mass, lurking in the frigid dark. This isn't just guesswork. The evidence is etched in celestial mechanics. Take Sedna, a dwarf planet so far out it takes 11,000 years to orbit the Sun. Its elongated path loops far beyond the Kuiper belt, yet something keeps it from wandering even farther. Then there's the peculiar alignment of 6 other extreme trans-Neptunian objects, their orbits all angled similarly, like compass needles pointing to an unseen magnet. Statistically, the odds of this happening randomly are less than 1 in 10,000. The culprit, a distant, undiscovered world tentatively dubbed Planet 9. But what is this shadowy giant? Theories split into 3 camps. The first and most straightforward: a rogue ice giant, ejected during the solar system's chaotic youth and now circling in a vast elliptical orbit. Simulations show early planetary shoving matches could have launched such a world into the outer darkness. The second idea is more exotic: a primordial black hole, no larger than a grapefruit but with the mass of a planet, its gravity warping orbits without emitting light. Some researchers even propose we could spot it by the gamma-ray flashes as dark matter annihilates in its crushing grip. Then there's the wild card: a captured exoplanet, stolen from another star during the Sun's infancy. Our galaxy is littered with orphaned worlds, and if one drifted close enough, the young Sun's gravity might have snared it. This could explain Planet 9's potential off-kilter orbit, unlike anything native to our solar system. The hunt is on. Japan's Subaru telescope, perched atop Mauna Kea, is meticulously scanning the outer solar system's twilight zone. With its wide-field optics, it's perfect for spotting the faint, slow-moving dot of a distant planet. Meanwhile, the Vera Rubin Observatory's upcoming sky surveys could catch its reflected sunlight by accident. If it exists, time is a factor. Planet Nine's hypothesized orbit could take up to 20,000 years to complete, meaning it might currently be at its farthest, dimmest point. But with every new Kuiper belt oddity discovered, like the recently spotted object with a 90-degree orbital tilt, the case for this hidden world grows stronger. Whether it's a misplaced ice giant, a stealthy black hole, or an interstellar immigrant, the answer wouldn't just solve a puzzle, it would rewrite the story of our cosmic neighborhood. In the darkest depths of space, some of the universe's most violent engines rage with unimaginable fury: quasars. These brilliant beacons, discovered in the 1960s as faint quasi-stellar radio sources, turned out to be anything but ordinary. Each one is the luminous heart of a young galaxy, powered by a supermassive black hole feeding on gas, dust, and even entire stars. But here's what defies logic. A single quasar, no larger than our solar system, can outshine its entire host galaxy by 1,000 times, blazing with the brightness of 1 trillion suns. How does something so compact produce such staggering energy? The answer lies in the physics of extremes. Picture a black hole with the mass of billions of suns, its event horizon stretching farther than Pluto's orbit. As matter spirals inward, friction heats it to millions of degrees, creating a swirling disk of plasma so energetic it glows across the electromagnetic spectrum: X-rays, gamma rays, visible light. Some of this material doesn't fall in. Instead, it's funneled into jets shooting outward at nearly light speed, carving through interstellar space like cosmic blowtorches. These jets can stretch for millions of light years, leaving scars visible billions of years later. What makes quasars even more fascinating is when they appear in cosmic history. The most distant, and therefore oldest quasars, date back to just 700 million years after the Big Bang, a blink in the universe's 13.8 billion-year lifespan. Their existence poses a thorny question: how did black holes grow so massive, so fast? Current models struggle to explain it. A seed black hole from a collapsing star would take far longer to reach such titanic proportions. Some theorists suggest direct collapse black holes formed in the early universe, skipping the star stage entirely when dense gas clouds imploded under their own weight. Others propose mergers of countless smaller black holes, piling up mass like a snowball rolling downhill. Quasars aren't just relics of a violent past. They're cosmic lighthouses, their light piercing through eons of space-time, carrying clues about the universe's youth. By analyzing their spectra, astronomers have found traces of the first heavy elements, proof that stars were already forging metals like carbon and oxygen when the cosmos was barely out of infancy. Even more remarkably, quasars helped solve one of the universe's greatest mysteries, the epoch of reionization. Their light reveals how the fog of neutral hydrogen that filled the early universe was burned away by the first generations of galaxies, clearing the stage for the transparent cosmos we see today. Yet for all their brilliance, quasars are fleeting. Their fiery outbursts last only 100 million years or so, a short phase in galactic evolution. Once the black hole exhausts its nearby fuel, the quasar dims, leaving behind a quieter beast like the one at the Milky Way's center. But in their prime, these cosmic powerhouses shaped everything around them. Their jets could trigger or suppress star formation across entire galaxies, their radiation sterilizing planetary systems light years away. Some researchers even speculate that quasar activity could have seeded the universe with elements necessary for life, their explosive death scattering enriched material far and wide. Today, telescopes like the James Webb Space Telescope are peering even farther back, hunting for the earliest quasars and the answers they hold. Each new discovery pushes the limits of our theories, forcing us to rethink how black holes, galaxies, and the cosmos itself came to be. Because quasars aren't just dazzling oddities, they're the universe's way of showing us how chaos and creation are woven together, how the darkest objects can light our path to understanding the past. The universe has a birthmark, a faint, cold whisper from its infancy known as the cosmic microwave background, or CMB. This afterglow of the Big Bang paints the sky in microwaves, a nearly uniform tapestry of tiny temperature fluctuations that tell the story of the cosmos' explosive beginnings. But in this sea of subtle variations, one anomaly stands out like a cosmic bruise: the CMB cold spot. Stretching across 1 billion light-years in the constellation Eridanus, this region is colder than the surrounding universe by about 70 microkelvin. That might sound negligible, but statistically, it's a 5 sigma outlier, an extreme fluke that challenges everything we think we know about the early universe. So what could cause such a massive cold patch? The leading explanation is a supervoid, an immense, mostly empty region of space where matter is so sparse, light passing through loses energy, stretching to longer, cooler wavelengths like a cosmic echo fading into silence. In 2015, astronomers using data from the Planck satellite and ground-based telescopes identified a potential candidate, a vast underdensity of galaxies dubbed the Eridanus supervoid. But here's the catch: this void, while enormous, isn't nearly large enough to account for the cold spot's temperature drop. It's like trying to explain a glacier with an ice cube. That discrepancy has sparked wilder theories. Some researchers propose the cold spot might be evidence of a collision with a parallel universe, a bubble of space-time brushing against our own in a multiverse landscape. The idea stems from eternal inflation theory, which suggests our universe is one of countless others in an endlessly inflating cosmic foam. If another bubble universe grazed ours in the distant past, the energy released could have left a scar on the CMB, cooling the surrounding space-time. It's a breathtaking possibility, but one lacking direct evidence. Not everyone's convinced. Skeptics argue the cold spot could be an artifact of statistical noise, a cosmic roll of the dice in an infinite universe where anomalies are inevitable. Others suggest more exotic physics, like textures, defects in space-time structure left over from the early universe's phase transitions, predicted by some grand unified theories but never observed. The Planck satellite's painstaking measurements only deepened the mystery. Its high-resolution data confirmed the cold spot's reality, but couldn't definitively link it to the supervoid or any known phenomenon. Even more perplexing, the spot's polarization patterns, the way its light waves are oriented, don't fully match theoretical predictions for a void or a collision. It's as if the universe left us a clue but scrambled the fingerprints. Future observatories like the Simons Observatory in Chile aim to study the cold spot with unprecedented precision, hunting for subtle distortions in its light that might reveal its origins. Whether it's a cosmic void, a bruise from a parallel universe, or something entirely unexpected, this icy anomaly reminds us that the universe's baby picture still holds secrets we've only begun to decode. And in those secrets might lie answers or even bigger questions about the nature of reality itself. On October 19, 2017, astronomers spotted something unprecedented, a visitor from another star system. Racing through our solar system at over 300,000 kilometers per hour, Oumuamua defied every expectation. This wasn't just another asteroid or comet. It was our first confirmed interstellar guest, a cosmic traveler from realms beyond our sun's influence. But its strangeness didn't end there. The more scientists studied it, the more baffling it became. For starters, its shape was unlike anything naturally occurring in our solar system. Initial observations suggested Oumuamua was elongated, possibly 10 times longer than it was wide, a cosmic cigar tumbling through space. Later analysis, however, revealed an even stranger silhouette, a flattened pancake-like disk. This unusual geometry alone made it an outlier. Most asteroids and comets are roughly spherical or irregularly lumpy. A shape this extreme hinted at a violent origin, perhaps a shard blasted free by a cataclysmic collision or a fragment of a shattered world. Then came the real head-scratcher, its motion. As Oumuamua sped away from the sun, it didn't follow the predictable path dictated by gravity alone. Instead, it accelerated slightly, as if pushed by an unseen force. For comets, this isn't unusual. Outgassing sunlight vaporizing ices, creating a natural rocket effect, can produce similar nudges. But here's the catch. Oumuamua showed no visible coma, no tail, no gas or dust escaping its surface. Telescopes scoured for signs of sublimating ice, yet found nothing. This absence of outgassing sparked a firestorm of theories. Some suggested Oumuamua was a rare, ultra-dense hydrogen iceberg, its gas evaporating invisibly. Others proposed it was a porous, fluffy aggregate of dust, light enough for solar radiation pressure to nudge it. Harvard astrophysicist Avi Loeb took the controversy further, floating the possibility that Oumuamua was artificial, a discarded light sail from an alien civilization, its thin, reflective surface catching the solar wind like a cosmic kite. While most scientists dismissed this as unlikely, the very fact it was debated underscores how truly peculiar this object was. The truth may lie in a middle ground. Recent simulations suggest Oumuamua could have been a chunk of nitrogen ice sheared off a Pluto-like exoplanet. Nitrogen outgassing would leave little trace in visible spectra but could explain the acceleration. Alternatively, it might be a fragment from a tidally disrupted planet, stretched and flattened by a distant star's gravity before being ejected into interstellar space. What makes Oumuamua so compelling isn't just its mystery, it's the timing. Its discovery revealed how little we know about the population of interstellar objects drifting through our galaxy. Since then, astronomers have spotted a second visitor, Comet Borisov, which behaved far more predictably. The contrast between the two only deepens Oumuamua's enigma. Was it a statistical fluke or a sign that interstellar space is filled with objects stranger than we've dared imagine? Telescopes like the Vera Rubin Observatory, set to scan the skies in the coming years, promise to find more of these nomadic wanderers. Each discovery will bring us closer to understanding whether Oumuamua was a cosmic oddball or the first glimpse of a vast, hidden diversity lurking between the stars. One thing's certain, its brief passage through our solar system left more questions than answers and rewrote the textbooks in the process. Our galaxy might seem like a tranquil island in the cosmic ocean, but its past tells a far more violent story, one of galactic cannibalism, mergers, and celestial conquest. Thanks to the European Space Agency's Gaia mission, we're now uncovering shocking details about the Milky Way's turbulent youth. Imagine a telescope so precise, it maps the positions, motions, and even the chemical fingerprints of over 1 billion stars. Gaia's data has revealed something astonishing. Our galaxy isn't just a collection of stars, it's a graveyard of ancient collisions, a patchwork of devoured dwarf galaxies whose remnants still swirl through the Milky Way's halo like cosmic ghosts. One of the most dramatic discoveries, the Gaia sausage. No, it's not a cosmic snack. It's the wreckage of a dwarf galaxy that smashed into the Milky Way around 8 to 10 billion years ago. Picture this galactic trespasser, roughly a quarter the size of our own galaxy, barreling inward on a doomed trajectory. The collision wasn't a gentle merger. It was a violent, head-on impact that shredded the dwarf galaxy apart, scattering its stars into chaotic, elongated orbits resembling, you guessed it, a sausage. These stars don't move like the rest of the Milky Way's inhabitants. Instead, they rocket around the galactic center on radial paths like bees trapped in a jar, their motions frozen in time as a testament to that cataclysmic encounter. But the Gaia sausage isn't just a fossil. It reshaped our galaxy forever. Simulations suggest this collision may have bulked up the Milky Way's thick disk, the region where older stars orbit in a puffed-up formation. Some researchers even speculate the impact triggered a burst of star formation, flooding the galaxy with new suns. The dwarf galaxy didn't just leave behind stars, it left its mark in the chemistry of our galaxy. Many of these captured stars are rich in alpha elements like magnesium and titanium, forged in the dwarf's short-lived massive stars before the merger. It's as if we're sifting through cosmic DNA, tracing the ancestry of our galactic neighborhood. Yet the sausage isn't the only intruder hiding in plain sight. Gaia's data has uncovered other stellar streams, ghostly rivers of stars winding through the Milky Way's halo, each the remains of a devoured companion. One of the most prominent is the Helmi stream, a group of stars with wildly inclined orbits, likely the debris of another dwarf galaxy swallowed billions of years ago. Then there's Sequoia, a possible sibling of the Gaia sausage, whose stars share similar chemical signatures but distinct orbits, hinting at multiple mergers around the same chaotic era. What makes these discoveries revolutionary isn't just the past they reveal, it's the future they predict. Our galaxy isn't done growing. Right now, the Milky Way is in the process of tearing apart the Sagittarius dwarf spheroidal, a small galaxy caught in a death spiral. Over time, its stars will dissolve into ours just like the Gaia sausage did, and in about 4 billion years will collide with the Andromeda galaxy, a merger so colossal it will reshape the night sky forever. These ancient mergers aren't just history, they're blueprints for how galaxies evolve, grow, and change over cosmic time. The Milky Way isn't a static island. It's a living, breathing entity built from the remains of countless smaller galaxies that dared to cross its path. Every time Gaia uncovers another stellar stream or oddball group of stars, we're peering deeper into our own cosmic ancestry, one violent, beautiful collision at a time. The universe is expanding. We've known that for nearly a century, but how fast it's expanding has become one of the most heated debates in modern cosmology. At the heart of the controversy lies the Hubble tension, a stubborn discrepancy that's forcing scientists to question whether we've misunderstood the cosmos itself. Here's the problem. When we measure the universe's expansion rate using nearby galaxies and supernova, we get one number. But when we study the afterglow of the Big Bang, the cosmic microwave background, we get a different number. These two methods, both rigorously tested, disagree by about 10%. That might not sound like much, but in a field where precision is everything, it's a glaring red flag. Let's break it down. The local method relies on so-called standard candles, celestial objects with known brightness, like Cepheid variable stars and Type Ia supernova. By measuring how their light stretches as space expands, astronomers calculate the Hubble constant, the rate of cosmic expansion. The latest results peg it around 73 kilometers per second per megaparsec. But when we look at the CMB, the relic radiation from the universe's infancy, the Planck satellite's data suggests a slower expansion, 67 kilometers per second per megaparsec. The gap between these values has only widened as measurements improve, ruling out simple errors. This isn't just academic quibbling. The Hubble tension threatens the foundation of the standard model of cosmology, our best understanding of how the universe works. One possibility, new physics, maybe dark energy, the mysterious force accelerating expansion, isn't constant as we've assumed. It could be growing stronger or evolving over time, subtly altering the expansion rate. Alternatively, there might be unseen types of neutrinos or exotic dark matter particles tweaking the universe's behavior in ways we haven't accounted for. Some theorists even propose an early dark energy phase, a brief surge of repulsive gravity in the universe's first moments that left fingerprints in the CMB but faded too quickly to affect modern measurements. Then there's the skeptic's take, systematic errors. Could there be hidden flaws in our measurements? Cepheid variables might be trickier to calibrate than we thought, or supernova could vary in ways we haven't caught. Even the CMB data isn't immune. Subtle biases in how we interpret its faint signals might skew results. But after years of cross-checking, no one's found a smoking gun. The tension persists. The stakes couldn't be higher. If new physics is required, it would mean rewriting textbooks. The James Webb Space Telescope is now joining the hunt, scrutinizing Cepheids and supernova with unprecedented clarity. Meanwhile, next-generation CMB experiments like the Simons Observatory aim to refine our snapshot of the early universe. Whatever the answer, the Hubble tension is more than a puzzle, it's a doorway. Beyond it could lie discoveries that reshape our understanding of time, gravity, and the very fabric of reality. And that's what makes science so thrilling. Sometimes the things that don't add up are the clues pointing us toward truths we haven't even dreamed of yet. Picture the most perfect sphere nature can create, not a flawless marble or a polished gem, but a city-sized star so dense, a teaspoon of its material would weigh 1 billion tons. Neutron stars, the collapsed cores of supergiant stars, are cosmic extremes where gravity crushes atoms into a sea of neutrons, leaving a remnant with almost unimaginable density. But here's the twist: despite their violent origins, these stellar corpses are smoother than anything else in the universe, with surface imperfections so tiny they make Earth's finest optics look like jagged rock. The secret lies in the physics of extremes. A neutron star's surface gravity is about 100 billion times stronger than Earth's, so powerful it flattens any irregularity into near-perfect smoothness. Even the largest deformities, dubbed mountains by astronomers, are barely a few millimeters tall. That's like scaling Everest down to the height of a grain of sand. These microscopic bumps form when the star's crust, a crystalline lattice of neutron-rich material, fractures under immense magnetic stress or uneven cooling. But gravity is relentless. Any protrusion taller than a few atoms risks collapsing under its own weight, sinking back into the quantum soup beneath. Yet these minuscule imperfections matter far more than their size suggests. Neutron stars often spin at dizzying speeds, some rotate hundreds of times per second, and even the tiniest asymmetry turns them into gravitational wave factories. As the star whirls, its mountains create ripples in spacetime, faint whispers detectable by observatories like LIGO and Virgo. The craziest part, these waves carry energy away, gradually slowing the star's spin in a process called braking. It's like a cosmic version of a spinning top losing speed due to air resistance. Only here, the air is the fabric of reality itself. But the real mystery isn't just how these mountains form, it's how tall they can be. Theoretical models suggest the crust could support features up to 10 centimeters high before gravity smashes them flat. That might not sound impressive, but on a neutron star, it's the difference between a gentle hill and a catastrophic landslide. Some researchers speculate that sudden crustquakes, stellar analogues of earthquakes, could briefly thrust these peaks higher, releasing bursts of gravitational waves. Others propose that accreted material from a companion star could pile up, creating temporary bulges before gravity smooths them away. Then there's the wild card, strange stars. A hypothetical cousin of neutron stars, these objects might be made of strange quark matter, a primordial soup where even neutrons break apart. If they exist, their surfaces could behave like infinite cliffs, with mountains vanishingly small or entirely absent. The hunt for such exotic objects isn't just academic, it could reshape our understanding of how matter behaves under conditions so extreme, even the laws of physics start to blur. Every gravitational wave detection, every pulse from a spinning neutron star, brings us closer to mapping these quantum landscapes. Future observatories like the Einstein telescope could spot deformities smaller than a virus, revealing the true limits of cosmic smoothness. Because in the end, neutron stars aren't just celestial curiosities. They're nature's ultimate physics labs where gravity, quantum forces, and spacetime itself collide, testing the very boundaries of what's possible. If black holes are the universe's ultimate one-way streets, white holes could be their bizarre cosmic counterparts, theoretical exits where nothing enters and everything escapes. Picture a black hole in reverse. Instead of pulling matter and light past the point of no return, a white hole violently expels them, spewing out energy and particles like a cosmic fire hose. The mathematics of general relativity allow for such objects, but detecting them is another story. They exist as tantalizing what-ifs at the edge of physics, challenging our understanding of time, gravity, and the very fabric of space-time. Some theories suggest white holes could be the other end of black hole tunnels, wormholes bridging distant regions of the universe. Imagine falling into a black hole and emerging from a white hole light years away, a shortcut through the cosmos. But there's a catch. Wormholes are notoriously unstable, prone to collapsing instantly unless propped open by exotic matter with negative energy, something we've never observed. White holes, if they exist, might be just as fleeting, blinking into existence for mere moments before vanishing. Then there's the Hawking connection. When black holes evaporate over eons through quantum processes, do they end with a whisper or a bang? Some models propose that a dying black hole could transform into a white hole in its final moments, releasing its stored energy in a sudden burst. This idea intertwines with loop quantum gravity, a framework where spacetime is granular, like a fabric woven from tiny threads. In this view, black holes might reach a point where gravity's crush reverses, rebounding into a white hole explosion. It's as if the universe itself hits a rewind button on collapse. The wildest speculation: the Big Bang itself might have been a white hole event, a primordial eruption of spacetime and matter from a singularity. Instead of a mysterious creation from nothing, our universe could be the aftermath of something collapsing and rebounding in a higher dimensional reality. This isn't just poetic symmetry, it's a testable hypothesis. If white holes exist, their signatures, brief, intense bursts of high-energy radiation, might lurk in astronomical data. Some researchers have even proposed that certain fast radio bursts or gamma-ray flashes could be white holes announcing their presence. Yet for all their theoretical allure, white holes face a glaring problem: entropy. The second law of thermodynamics insists disorder must increase, but a white hole's spontaneous orderliness, spitting out pristine energy, seems to defy this. Unless, of course, their outbursts are the universe's way of balancing the books, with black holes soaking up entropy elsewhere. Whether cosmic myths or hidden giants, white holes force us to confront the limits of relativity and quantum mechanics. They're reminders that the universe's strangest possibilities often lurk in the equations we've yet to fully decipher. And if we ever find one, it wouldn't just rewrite astrophysics, it would redefine our understanding of time itself. If you could zoom in on spacetime itself, past atoms, past subatomic particles, down to scales a billion trillion times smaller, you wouldn't find emptiness. You'd find chaos, a seething, frothing turbulence where space and time lose all semblance of order, bubbling like a boiling pot of water. This is quantum foam, the universe's smallest possible scale, where the very fabric of reality becomes a probabilistic storm. At these unimaginably tiny distances, around 1 Planck length, or 10 to the minus 35 meters, Heisenberg's uncertainty principle reigns supreme. Energy fluctuates wildly, borrowing from the vacuum itself to create pairs of virtual particles that pop in and out of existence in fractions of a nanosecond. These aren't just mathematical quirks, they're the reason empty space isn't truly empty. Even in a perfect vacuum, particles and antiparticles flicker into being, annihilating each other so quickly we can only detect their ghostly effects, like the Casimir force or Lamb's shift in atomic spectra. But quantum foam takes this further. Here, space-time itself writhes, with microscopic wormholes and bridges forming and dissolving in the chaos. The implications are staggering. Some theories suggest these fleeting wormholes could connect distant regions of space-time, threading the universe with shortcuts smaller than an atom. Others propose that foaminess might blur our view of distant quasars or gamma-ray bursts, as high-energy photons get jostled by the froth on their billion-year journeys. Then there's the holographic principle, which posits that all the information in a volume of space might be encoded on its boundary, a cosmic pixelation hinting that reality itself could be a projection from this underlying quantum turbulence. But how do you test something so infinitesimal? Enter the holometer experiment at Fermilab. This audacious device isn't a traditional telescope or particle collider. It's a laser-powered ruler sensitive enough to detect spacetime's hypothetical graininess. By splitting laser beams and measuring their interference patterns with insane precision, scientists hope to catch spacetime jittering as quantum foam bubbles shifted beneath their feet. The result: silence. No foam detected, at least not at the scales holometer could probe. But that's science. Every null result narrows the possibilities, pushing the frontier of what we know. Quantum foam isn't just a curiosity, it's where relativity and quantum mechanics collide, where our understanding of gravity and particles breaks down. If spacetime has a texture, if wormholes flicker in the dark, it could reshape everything from black hole physics to the fate of the universe, the wildest part. We might be standing on the shore of this foam right now, our bodies and the air around us perforated by wormholes too small to see, a hidden turbulence stitching reality together one Planck-length bubble at a time. Among the most unexpected planetary systems ever discovered are the worlds orbiting a cosmic corpse, a pulsar known as FRB 1257+12. This rapidly spinning neutron star, located 2,300 light-years away in the constellation Virgo, shouldn't have planets at all. After all, pulsars are born from violent supernova, explosions so powerful they can obliterate any nearby worlds in an instant. Yet in 1992, astronomers Alexander Wolskson and Dale Frail made a jaw-dropping announcement. They'd found not one, but 3 planets circling this stellar zombie. The discovery shattered expectations. Pulsars are the remnants of massive stars that have exhausted their fuel and collapsed under their own gravity, triggering cataclysmic explosions. The sheer force of a supernova should have vaporized any pre-existing planets, leaving nothing but scorched debris. So how did these worlds survive? One theory suggests they weren't survivors at all. They were born from the ashes. When the star went supernova, some of the ejected material might have fallen back into orbit, forming a disk of rubble around the pulsar. Over time, this debris coalesced into new planets forged in the aftermath of destruction. But the strangeness doesn't end there. These pulsar planets are unlike anything in our solar system. Their compositions are a cosmic alchemist's dream. Think diamond cores larger than Earth, forged under extreme pressure from the pulsar's intense gravity and radiation. Imagine a world where the ground beneath your feet isn't rock but crystallized carbon, glittering under the eerie glow of a spinning neutron star. The conditions are so extreme that some models suggest these planets could even have metallic hydrogen oceans, exotic states of matter impossible to replicate on Earth. Then there's the question of habitability or lack thereof. Pulsars emit deadly beams of X-rays and gamma rays, sweeping through space like cosmic lighthouse beams. Any life as we know it would be instantly sterilized by this radiation. Yet, some scientists speculate about the possibility of underground life, sheltered beneath miles of diamond crust, tapping into geothermal energy from the planet's core. It's a wild thought, life forms evolving in the shadow of a dead star, adapted to conditions we can scarcely imagine. The most intriguing part, these pulsar planets might not be rare. Since the first discovery, astronomers have spotted other pulsar systems with possible planetary companions, suggesting that these bizarre worlds could be more common than we thought. Each detection challenges our understanding of how planets form, pushing the boundaries of what we consider possible in the cosmos. What began as an astronomical oddity has reshaped planetary science. Pulsar planets force us to rethink the resilience of worlds and the chaotic processes that shape planetary systems. They're a testament to the universe's creativity, turning the aftermath of a stellar explosion into something as wondrous as a diamond world spinning in the dark. And who knows, out there among the dead stars, there may be even stranger worlds waiting to be found. The universe is supposed to expand uniformly, with galaxies drifting apart like raisins in rising dough. But something bizarre is happening on the largest scales, a mysterious current sweeping entire galaxy clusters in the same direction at staggering speeds. Astronomers call it dark flow, and its existence suggests an unsettling possibility. Our observable universe might be tugged by something massive and completely unseen. This isn't just a subtle drift. Studies of hundreds of galaxy clusters, using the kinetic Sunyaev-Zeldovich effect to map their motions, reveal a coordinated movement toward a single patch of sky near the constellations Centaurus and Hydra. These clusters are racing at nearly 1,000 kilometers per second, far faster than cosmic expansion can explain, as if pulled by a gravitational force beyond the edge of our cosmic horizon. The culprit: either our understanding of cosmology is fundamentally flawed, or there's something out there, something so colossal, it defies observation. Here's where it gets wild. One leading theory suggests dark flow could be evidence of a pre-Big Bang structure, a relic from a time before our universe began. Imagine the cosmic equivalent of a tidal bulge, left behind by a neighboring universe brushing against ours during an inflationary phase. Alternatively, it might point to a supermassive parent universe exerting gravitational influence on our bubble-like domain in a multiverse landscape. These ideas aren't just speculation. They're grounded in controversial Planck satellite data that initially detected, then debated the statistical signatures of this flow. Skeptics argue it could be a systematic error, an artifact of how we measure cosmic microwave background distortions. Others propose less exotic explanations, like local superclusters we've yet to map fully. But the persistence of dark flow across multiple studies keeps the mystery alive. If real, it would mean the cosmos isn't just expanding, it's also swimming in a hidden current, one that might lead to realms beyond our wildest theories. Until we peer deeper, dark flow remains a ghostly whisper from the edges of existence, hinting that the universe's greatest secrets lie just out of sight. Most galaxies huddle together in clusters or filament-like cosmic webs, gravitationally bound in bustling stellar metropolises. But imagine a galaxy so isolated, its nearest neighbor is over 100 million light-years away, a lone island adrift in an ocean of nothingness. Meet MCG plus 01020015, one of the loneliest galaxies ever discovered. Floating in a void spanning nearly 200 million light-years, this solitary spiral has more empty space around it than any other known galaxy. It's not just remote, it's marooned in the cosmic equivalent of a desert where the density of matter is less than 1% of the universe's average. What makes void galaxies like this so fascinating is how they defy expectations. According to standard models, galaxies form where gas and dark matter cluster together, growing through mergers and accretions over billions of years. But in these desolate voids, there's barely any raw material to work with. MCG plus 01020015 shouldn't exist, or at least it shouldn't have formed as a well-defined spiral. Yet there it is, spinning quietly in the dark, its stars burning against near-total blackness. The struggle to survive in such extreme isolation shapes these galaxies in bizarre ways. With no nearby neighbors to steal gas from or collide with, void galaxies rely entirely on their own limited reservoirs of hydrogen to forge new stars. But even that process is strained. The sparse surroundings mean fewer cosmic filaments funnel fresh gas inward, leaving these galaxies starved for fuel. As a result, many void galaxies exhibit stunted star formation, either burning through their gas too quickly in short, intense bursts or fading into slow, quiet decline. Some become red and dead far sooner than their cluster-dwelling counterparts. their star-forming engines sputtering out from sheer loneliness. Yet against all odds, some void galaxies like MCG plus 0102015 manage to thrive. Observations reveal patches of vigorous star birth, suggesting these isolated systems might harbor denser, more efficient pockets of gas than expected. It's possible their extreme environments force unconventional evolutionary paths, perhaps compressing gas into tighter, more productive regions or triggering unique internal mechanisms that sustain star formation longer than models predict. The existence of void galaxies forces astronomers to rethink fundamental assumptions. If galaxies can form and persist in near-total isolation, does that mean our theories overemphasize the role of environment? Or could there be unseen processes, flows of dark matter, hidden gas streams, or primordial density fluctuations that give these lonely outliers a fighting chance? Every new void galaxy discovered adds another piece to the puzzle, proving that even in the emptiest corners of the universe, nature finds a way to defy the odds. And there's something haunting about that. These solitary islands of light aren't just cosmic curiosities, they're testaments to resilience, shining proof that even in the vast, indifferent void, the spark of creation flickers on. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate shredders. At least that's what Stephen Hawking once thought. Back in the 1970s, he made a startling claim: black holes don't just swallow matter and light. They erase information itself. Picture tossing a book into a fire. The pages burn, but the smoke and ash still carry traces of what was written. Now imagine that fire obliterates every single trace, the very memory of the book's existence. That's the heart of the black hole information paradox, and it threatens to upend our understanding of reality. Here's the problem. Quantum mechanics insists information can never be truly destroyed. It might get scrambled, hidden, or encoded, but it can't vanish without a trace. Yet black holes, according to Hawking's calculations, evaporate over time, slowly leaking away as ghostly radiation. If that radiation carries no imprint of what fell in, the information is lost forever. Physicists were left with an impossible choice. Either quantum theory is wrong, or our grasp of black holes is missing something profound. Enter the holographic principle, one of the most mind-bending ideas in modern physics. It suggests that all the information swallowed by a black hole isn't destroyed. It's smeared across its event horizon like a cosmic etch-a-sketch. Think of it this way: a three-dimensional object casts a two-dimensional shadow. In the same way, the holographic principle argues that everything inside a black hole might be encoded on its surface, preserved in Planck-scale pixels we don't yet understand. If true, information isn't lost, it's transformed, written in a language of quantum bits we're still decoding. But how does it escape? That's where things get wild. Some theories propose black holes sprout soft hair, infinitesimally low energy particles near the event horizon that record infinitesimal details about what falls in. These aren't literal hairs, of course, but quantum imprints subtle enough to preserve information without violating known physics. Others suggest more violent solutions, like the firewall paradox. Imagine reaching the event horizon, expecting to cross it smoothly only to hit a searing wall of energy, a quantum inferno that scrambles your information onto the surface before you're vaporized. It's a radical idea born from the clash between quantum mechanics and general relativity. The debate rages on. Experiments like gravitational wave detections and quantum simulations inch us closer to answers, but the paradox remains unsolved. What's at stake isn't just black holes, it's the bedrock of physics itself. If information can vanish, our laws of cause and effect crumble. If it's preserved in ways we can't yet see, the universe might be far stranger, far more holographic than we ever dreamed. One thing's certain: the black hole information paradox isn't just a puzzle. It's a gateway to a deeper reality waiting beyond the event horizon. The cosmic microwave background should be the ultimate cosmic fingerprint, a perfectly random snapshot of the universe's earliest moments. Yet when scientists stared deep into its patterns, they found something unsettling. The universe appears to have a preferred direction, an axis where temperature fluctuations mysteriously align with the plane of our solar system. Astronomers call this eerie correlation the axis of evil, and it's either the most bizarre coincidence in cosmology or a clue that our universe isn't as impartial as we thought. This discovery shook the foundations of modern cosmology because it violates the Copernican principle, the idea that Earth holds no special place in the cosmos. When the Planck satellite mapped the CMB's temperature variations with unprecedented precision, it revealed a curious asymmetry. Hotter and colder patches weren't distributed randomly. Instead, they seemed to loosely mirror the ecliptic plane, the imaginary disk where planets orbit the Sun. The odds of this happening by chance, less than 1 in 1,000. It's like rolling a die 100 times and always getting numbers that mysteriously correspond to your birthday. Some researchers dismiss this as a statistical fluke, a cosmic Rorschach test where humans see patterns in randomness. Others propose more mundane explanations, like subtle errors in how we subtract the Milky Way's foreground glow from CMB data. But the most radical theories venture into uncharted territory. What if this alignment isn't an error but an imprint from before the Big Bang? Certain models of conformal cyclic cosmology suggest our universe might be one in an endless chain, with each new cycle inheriting faint traces from its predecessor. In this scenario, the axis of evil could be a cosmic scar, a relic of some pre-Big Bang structure that subtly biased the newborn universe's expansion. Then there's the multiverse angle. If we're part of a vast ensemble of bubble universes, each with different physical laws, our local patch might have been nudged by gravitational waves or quantum entanglement from a neighboring bubble. This could have tilted primordial density fluctuations, leaving a faint directional bias frozen into the CMB. It's a controversial idea. Many physicists argue such influences would have been wiped out by inflation, but the possibility lingers. The debate rages because the implications are staggering. If the axis of evil is real and not an artifact, it means the universe has a hidden architecture, a subtle grain like cosmic wood where the rules might vary depending on which way you look. Future CMB experiments, like the Simons Observatory, aim to settle the controversy with even finer measurements. Until then, this celestial oddity remains either a cautionary tale about human pattern seeking, or the first faint whisper of a reality far stranger than we've dared to imagine. In the vast tapestry of the cosmos, some galaxies don't play by the rules. They're the phantoms of deep space, so faint and wispy they barely register against the blackness. Ultra-diffuse galaxies, or UDG, are cosmic enigmas stretching as wide as the Milky Way but containing just 1% of its stars. Imagine a ghostly haze of starlight, so sparse you could fly through it for thousands of light years without seeing a single sun. Yet despite their ethereal appearance, these galaxies hold some of the universe's most perplexing secrets, challenging everything we thought we knew about how galaxies form and evolve. Take Dragonfly 44, a UDG lurking in the Coma cluster. At first glance, it's unremarkable, a smudge of dim light in a crowded galactic neighborhood. But when astronomers measured its motion, they got a shock. The stars within it were whirling so fast that, by all rights, the galaxy should have torn itself apart. The only explanation, a monstrous halo of dark matter, weighing as much as the Milky Way's but spread far more diffusely, its invisible grip keeping the stars from flying off into the void. Dragonfly 44 is 99.99% dark matter, a celestial mirage where the unseen outweighs the visible by a factor of 10,000. But here's the twist, not all UDGs follow this script. Some, like NGC 1052 DF2, defy expectations entirely. they're missing dark matter almost completely, their stars drifting like unmoored ships with nothing anchoring them in place. This discovery sent shockwaves through astrophysics. If dark matter is the scaffolding that holds galaxies together, how could these ghostly giants exist without it? One theory suggests they're failed galaxies, born in environments so devoid of dark matter they never fully coalesced. Another proposes they're galactic remnants, stripped of their dark halos by violent encounters with larger neighbors, leaving behind skeletal husks of stars. Then there's the formation mystery. How do these faint behemoths even come to be? Some might be ancient relics forming in the early universe when gas was too sparse to birth many stars. Others could be the result of galactic harassment, repeated collisions in crowded clusters that stretch galaxies into gossamer-thin forms. There's even a wild card, tidal dwarf galaxies, born from debris ripped free during galactic collisions, which might explain the ones lacking dark matter. The problem, these should be rare, yet UDGs are everywhere, from isolated voids to dense clusters, as if the universe has a hidden factory producing them en masse. The implications stretch beyond astronomy textbooks. If UDGs can exist with or without dark matter, they force us to question whether our theories about galaxy formation are incomplete, or if dark matter itself behaves in ways we haven't yet imagined. Telescopes like the James Webb Space Telescope and the upcoming Vera Rubin Observatory are hunting for answers, peering into the faintest corners of the sky to uncover more of these cosmic ghosts. One thing's certain, ultra-diffuse galaxies are more than just oddities. They're cosmic stress tests pressing at the boundaries of our understanding. Whether they're dark matter dominions or ethereal anomalies, they remind us that the universe has a flair for the unexpected, crafting mysteries where we least expect them, in the faintest whispers of starlight. Time crystals sound like something ripped from a physicist's wildest dream, structures that break the most fundamental symmetry of nature, time itself. Unlike any other form of matter, these bizarre quantum systems don't settle into equilibrium. Instead, they pulse rhythmically, cycling through states without absorbing or losing energy, like a perpetual motion machine operating within the strictest laws of physics. First proposed by Nobel laureate Frank Wilczek in 2012, time crystals weren't just theoretical curiosities. By 2017, they'd been forged in labs, using chains of ions or diamond impurities manipulated with lasers, proving that matter could indeed exist in this strange fourth-dimensional phase. The secret lies in their quantum choreography. Ordinary crystals, like diamonds or salt, have atoms arranged in repeating patterns in space. Time crystals take this further. Their atomic structures repeat not just in space but in time, oscillating between configurations at fixed intervals without any energy input. Think of it like a clock that ticks forever without winding, its gears turning solely through the quantum equivalent of inertia. This behavior defies classical thermodynamics, where systems should always trend toward disorder. Time crystals, by contrast, lock into a rhythm that resists entropy's pull, a dance dictated by quantum entanglement and many body interactions. Creating them demands extreme precision. In one breakthrough, researchers used ytterbium atoms arranged in a ring, zapping them with alternating laser pulses to induce a periodic flip in their quantum spins. The astonishing result, the spins flipped at half the frequency of the laser pulses, a telltale sign of time translation symmetry breaking, the hallmark of a time crystal. It's as if you pushed a pendulum every second, only for it to swing back every 2 seconds instead, a defiance of classical intuition. These experiments didn't just validate Wilczek's idea, they opened the door to a new frontier in condensed matter physics. But why does this matter beyond the lab? For starters, time crystals could revolutionize quantum computing. Their inherent stability against decoherence, the bane of quantum bits, makes them ideal candidates for error-resistant memory storage. Imagine quantum processors that don't crumble at the slightest disturbance, their data encoded in the unshakable rhythms of time crystals. There's even speculation about their role in cosmology. Some theories suggest the early universe might have undergone a time crystal-like phase, its fabric oscillating in ways that seeded the large-scale structure we see today. The cosmic implications are dizzying. If time crystals can exist naturally, perhaps in the extreme conditions near neutron stars or in the quantum vacuum itself, they might hint at entirely new states of matter lurking in the universe's most hostile environments. Or consider the philosophical ripple effects. A structure that bends time's symmetry challenges our very notions of causality and equilibrium, suggesting that the arrow of time might not be as rigid as we thought. For now, time crystals remain fragile, fleeting creations, bound to ultra-cold labs and carefully tuned lasers. But their existence proves that the universe still has surprises up its sleeve, that even within the ironclad rules of physics, there's room for materials that tick to their own eternal beat. And if we've learned anything from their discovery, it's that the line between science fiction and scientific reality is thinner than we ever imagined. From ghostly dark matter to time-defying crystals, these 25 cosmic mysteries are more than just puzzles, they're invitations. Invitations to explore, to question, to stand at the edge of human knowledge and peer into the unknown. We've traveled through invisible forces bending galaxies, voids so vast they defy logic, and black holes that might erase reality itself. Yet with every answer we uncover, the universe reveals 10 new questions, each more thrilling than the last. Think about it, dark matter's gravitational fingerprints surround us, yet we still don't know what it is. Fast radio bursts scream across the cosmos, but their sources remain a riddle. The wow signal taunts us with its fleeting whisper. Was it a cosmic accident or something more? Even our own solar system hides secrets, from the hypothetical planet 9 to the enigmatic Oumuamua, a visitor from interstellar space that defied every expectation. And who could forget the Fermi Bubbles towering over the Milky Way like silent sentinels of some ancient cataclysm? Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That's the heartbeat of astronomy. Every flicker of starlight, every anomalous signal, every unexplained motion in the void is a clue, a breadcrumb trail leading us deeper into the universe's grand story. The cosmos doesn't give up its secrets easily. It challenges us, dares us to think bigger, to build better telescopes, to question our assumptions. So here's my question for you. Which of these mysteries keeps you up at night? Is it the chilling possibility of rogue black holes drifting unseen through our galaxy? The spine-tingling notion that dark energy might one day rip spacetime apart? Or maybe it's the haunting beauty of ultra-diffuse galaxies, ghostly and half-formed, floating in the cosmic dark? Drop a comment below. I'd love to hear which cosmic enigma sparks your curiosity. Because the best part of science isn't having all the answers. It's the shared wonder of the search, the collective thrill of not knowing yet. The universe is vast, strange, and brimming with secrets. And somewhere out there, hidden in the noise of the cosmos or the equations we've yet to write, the next great discovery is waiting. All we have to do is keep looking. What if our universe isn't the ultimate reality, but someone else's simulation? It sounds like science fiction, but some of the cosmic oddities we've explored take on a chilling new light when viewed through the lens of the simulation hypothesis. Think about it, inexplicable anomalies like the CMB cold spot, quantum entanglements, spooky action at a distance, or even dark matter's invisible grip could in theory be glitches or shortcuts in an ultra-advanced computational reality. The idea isn't new. Philosopher Nick Bostrom laid out a trilemma in 2003. Either civilizations never reach post-human stages capable of running ancestor simulations, they choose not to, or we're almost certainly living in one. Consider the evidence, or lack thereof. quantum mechanics already paints reality as probabilistic, with particles existing in superposition until observed. Could this wave function collapse simply be a rendering optimization, like a video game loading details only when a player looks? Even the universe's pixelated edge, the Planck length, hints at a potential resolution limit, a cosmic pixel size for whatever hardware runs our reality. And then there's the Fermi paradox. If the universe teems with potential for life, where is everyone? One unsettling answer: the simulation's designers didn't bother populating it beyond our local dataset. But the most tantalizing clues might lurk in physics' unsolved puzzles. Take the unreasonable effectiveness of mathematics in describing the cosmos. Why should nature obey elegant equations unless those rules were coded that way? Or ponder the fine-tuned constants: gravity's strength, the speed of light that, if tweaked slightly, would make life impossible. In a simulation, these could be deliberate parameters set by the programmers. Even quantum foam's chaotic turbulence might resemble the background noise of a system processing near its limits. Not everyone's convinced. Critics argue the hypothesis is unfalsifiable, a cosmic what-if with no testable predictions. Yet some scientists are trying. Physicist Silas Bean proposed that simulators might cut corners by imposing a lattice structure on high-energy particles, something future experiments could detect. Others suggest looking for rounding errors in physical constants at extreme scales, like cosmic rays behaving oddly near energy thresholds. Whether you find the idea thrilling or unsettling, the simulation hypothesis forces us to confront fundamental questions about reality's nature. It's the ultimate meta-mystery, a hall of mirrors where every cosmic anomaly might be a bug, a feature, or something beyond our current comprehension. So the next time you gaze at the stars, ask yourself, are we explorers in a boundless universe or players in a cosmos-sized game we've only begun to debug? The answer, or lack thereof, might be the greatest mystery of all.